Swayam Prabha. Digital India. Educated India.
We saw that there are 4 concepts in mechanics and 4 equations that connects them, right. That is what we have been looking at. So, we have seen all the 4 concepts, we have seen what force is, we have seen what displacement is, and then we have seen now what strain is, and we have seen what stress is, right. So, we have seen the equation that connects the displacement to the strain. So, the strain and displacement relation to be 1 half H plus H transpose, and then we have seen the equation that connects the stress and the force, which is equilibrium equations. Which is divergence of sigma plus rho b equal to rho a and sigma equal to sigma transpose. You have seen these equations. Now, what you are going to see is the equation that connects the strain to the displacement, that is the compatibility condition. Okay. This is what we are going to look at now. Now, what did we say about the displacement field? We said that displacement field would be in such a way that if I have a surface, the surface will move like this, but there will not be opening up of surfaces or there will not be interpenetration of surfaces, right. That is, a material particle will be mapped on to a material particle in the current configuration. There will not be a case where a material particle becomes 2 different material particles, or there will not be a case where 2 different material particles will become fused to a single material particle. Okay. So, that is what we said about the displacement field. If that were to be the case, then what you know is the order of differentiation of the displacement field will not matter. Okay. Mathematically, what this means is, if you have dou square u x by dou x dou y, this will be same as dou square u x dou y dou x. Okay. That is, the order in which you differentiate the components of the displacement field will be immaterial, because it is a smooth continuous displacement field. Okay. So, what happens then is, now I have 6 components of strain that I can prescribe, from which I have to find only 3 components of the displacement field. So, there is a disparity in the number of unknowns. Okay. So, what will happen is there will be a restriction on how I can prescribe the components of the strain, because this prescription of the components of the strain should be consistent, so that I find a smooth continuous displacement field from the prescribed strain components. To give you an idea, let us look at the plain strain case. Let us assume the strain is given by epsilon x6 function of x comma y, epsilon xy some function of x comma y, 0, epsilon xy some function of x comma y, epsilon yy some function of x comma y, 0, 0, 0, 0. Okay. Say I prescribe this epsilon x6, epsilon xy and epsilon yy. Now, from this prescription I have to be able to find the components of the displacement ux and uy. So, for this I will have the displacement field as u to be ux function of x comma y ex plus uy function of x comma y E y, so that epsilon x x becomes dou u x by dou x, epsilon y y becomes dou u y by dou y, and epsilon x y becomes 1 half dou u x by dou y plus dou u y by dou x. This comes from the fact that I have used this in here to compute the strain components in terms of the displacement field. Okay. Now, let us take forward these equations. I add epsilon x x as dou u x by dou x, I add epsilon y y as dou u y by dou y, I add epsilon x y as 1 half dou u x by dou y plus dou u y by dou x. Now, let us compute dou square epsilon x y by dou x dou y. What is this going to be? This is going to be 1 half dou cube u x by dou x dou y square plus dou cube u y dou x square dou y. Here again I use the fact that dou x dou y dou x are used dou cube u y by dou x dou y dou x can be written as dou cube u y by dou x square dou y, since u of y is smooth and differentiable. Okay, it is sufficiently smooth and differentiable, because I should have second derivatives, third derivatives of u of y possible. Okay, sufficiently smooth and differentiable. Okay. Now, what is this? What is 2 times dou square epsilon x y by dou x dou y? This is nothing but dou square epsilon x x by dou y square plus this dou square epsilon y y by dou x square. Okay. So, basically what you have obtained is a differential equation connecting the components of the strain, right. Differential equation connecting the components of the strain. Okay. So, this is called as compatibility condition. Okay. If the displacement field is sufficiently smooth and differentiable, there will exist some relationship between the components of the strain. Only prescriptions of strain satisfy those relationships or admissible strain fields. Okay. So, that is what the compatibility condition tells us. This is if I assume the strain is plane in terms of x and y directions. Similarly, I can write the condition for the strain being plane in terms of the other 2 planes. Okay. So, if the plane is plane in the xz plane, I will have epsilon xz divided by dou x dou z to be given by dou square epsilon xx by dou z square. By I am writing this by analogy, which you can show also will hold true in the real case. Okay. Epsilon zz by dou x square, and similarly I have dou square epsilon yz by dou y dou z to be equal to dou square epsilon yy by dou z square plus dou square epsilon zz by dou y square. Okay. So, this is if the strain is plane in the x and z coordinate or the strain is plane in the y and z coordinate. Okay. Apart from this, the general set of compatibility conditions in 3 dimensions, I will not derive this. Is in general represented as curl of epsilon being equal to 0, only 6 of them would be independent. Okay. Those 6 are the 3 that are listed here is one set of equations, the other equations are what I will give now. The z and the 3 equations that we had before were so these are the compatibility conditions. So, these 6 equations are the compatibility conditions. Okay. Now, since strain is a symmetric tensor, you can write epsilon xy is equal to epsilon yx. So, I am not bothered about being precise about writing xy or yz or xz. Okay. So, either way you can write it is a symmetric tensor. It is for the same reason that when you look at the angle change A daughter with B between A and B, this will be 2 times epsilon A daughter with B divided by sine of theta ref. From the definition of transpose, this will be same as 2 times epsilon b dot with A divided by sine of theta rf. So, it does not matter with what vector you prefix the epsilon, okay. It does not matter on what vector the linearized chain acts, this will be same because epsilon is equal to epsilon transpose by the way we have defined epsilon as, okay. Okay. So, we have seen what a compatibility condition now is. So, the only equation that is remaining is going back to this chart, we have to connect the stress and the strain. The equation that connects the stress and the strain is called as the constitutive relation, okay.